Did you learn some formula for the determinant that was like complicated and maybe you didn't understand why you were doing it? I'm going to break down exactly what's going on. Really what we're doing is multiplying vectors together. I'm going to use this heart symbol. It's going to be a lot of fun. If you watch my last video, every matrix encodes a transformation, and the determinant, in this case it's 7, records how much the area changes by when we do it. In 3 dimensions, the determinant is measuring how the volume is changing. Now, unfortunately, finding a formula for that is really complicated. As we go from size 2 to size 3, things get complicated, but I want to show you that this isn't coming out of thin air. I'm going to show you that there's a way to define a weird multiplication of vectors, but when we do it, we get the determinant as an answer. And so if I want 2 by 2 or 3 by 3, just multiply the columns together and see what you get. By the way, I'm a professional mathematician. All of this can be made rigorous, so ask comments if you want to know more. So I'm going to explain what properties a multiplication should have, but one for sure is a distributive property. But this multiplication has weird properties too. For instance, anytime you have a matrix with 2 identical vectors, it's going to collapse the area or volume down to 0. So whatever vector I put in this matrix, the determinant has to be 0. If we're going to find the determinant by multiplying things together, that means any vector times itself has to be 0. Let's add that to our list, and actually let's see it in action. If it's really true that any vector times itself has to be 0, then this vector times itself has to be 0. But if I expand all this out using the distributive property, notice what I get. Some of these terms are going to be 0, like that times itself, and w times itself, those are going to vanish. And so what I have is this wonderful equation that v heart w plus w heart v has to be 0. If I simplify this equation a little bit, I see that if I heart 2 vectors in the opposite order, one has to be the negative of the other. I told you this was a weird multiplication. It turns out this is all you need to calculate determinants. Let's see it in action. Actually, I lied. There's one more thing we need. If we take the determinant of the identity matrix, we should always get 1 because area is not going to change. So let's find the determinant of that matrix from earlier. The answer should be 7. I'm going to take the first column and write it out in this way using I and j. That's just the first and second coordinate. And then I'm going to expand everything using the distributive property. Notice that that and that are 0 because they're something hearted with itself. And now notice that these are the same terms, but the order is switched. And we learn that whenever we multiply in the opposite order, we have to change the sign. I can replace this by I heart j if I make that a plus 3. And now I've got like terms, and so I've got 7 times I heart j. But what is I heart j? Well, that would just be the determinant of the matrix 1, 0, 0, 1, the identity matrix. So this thing here is just going to equal 1, and we got our wonderful number 7. Pause the video to check what happens in general, but now we start to see where the AD minus BC formula comes in, just from multiplying these things together and using that negative sign when you switch the order. The idea is the same for 3 by 3 or bigger. Anytime you heart the same thing together, you're going to get 0. And so of the 27 possible terms when you expand, only 6 of them are going to survive. They're the things where you have some I, some j, and some k in some order when you FOILed things out. For instance, if I wanted to find I, k, j, I would just multiply those 3 numbers together. When I put all the numbers in, you might start to notice something. For instance, these two both involve an I in the first coordinate, and then when we think about what's happening in the second coordinate, we're actually multiplying those cross entries there. This is where that rule of expansion by minors is coming from. It's the same thing down here with this k. The numbers -4 and -20 are coming from multiplying 2 times 2 and 4 times 5. Pause the video and check out the other expansions and see what you get. Now we got lucky that some of our coefficients were 0, so we don't need to write those down, but all the other ones we need to readjust the order so that they're all I, j, k, so we can combine like terms. For instance, here I've got j times I, and I want to switch it over to I times j. Anytime I switch the order, I introduce a minus sign. I did the same thing down here. These guys are all straightened out, but I still need a bit more work down here. Continuing that work, I can swap the j and the k here, and maybe the I and the k here, and slowly I'm putting things into order. If you've ever seen a definition that used the word permutation, that's really what's going on. Once all the dust settles, we get everything in the term ijk and the number 10, and that's exactly what the determinant is. Do mathematicians really use the heart symbol? No, but I wish they would. But actually what they use is pretty close to a heart. They use this upside down V symbol, and it's called an exterior product. And so now you know why a determinant is just a weird multiplication.